Hello everyone, welcome to this video. Today we would be using an example to demonstrate how we can flash Simulink models on the Arduino board. For this example, we would be trying to blink two different LEDs alternatively, and the frequency of their blinking would be controlled using a joystick module. Now the interesting part here would be, first we would develop the logic in Simulink, run the simulation, and then do some minor modifications in the model, flash the same model on the Arduino board after generating an executable file out of it. Once the model is flashed on the Arduino board, we would interface the board with the necessary hardwares like joystick module, LEDs, etc. And then see how we can control the blinking frequency using the joystick. So let's start. For the purpose of this video, I have the model ready right here. This is the joystick input which we would be providing using this slider control. Before going into that, let's understand what type of output the joystick module would provide us. It basically has three different outputs. One is the position along the y-axis, one is the position along the x-axis, and the other is a switch output, which if the joystick button is pressed, it will send it as 1. Here in this model, we are only utilizing the output which it gives as the y-axis, that is its position along the y-axis. Now at its resting position, that is the normal position of the joystick switch, the output which it sends is the value 523, and the range of its values is from 0 to 1023, where 0 is along the extreme negative y and 1023 is at the extreme positive y. The resting place, as I said, is 523. Now for this model, we want that the resting position should be actually a 0 value, so that we have subtracted an offset of 523 here from the joystick input, so that the resting position is set as 0. Accordingly, the extreme minus y would become 0 minus 523, that is minus 523, and the positive extreme along the y-axis would become 1023 minus 523, that is 500. So those will be the output here, maximum and minimum output. Now here we are just scaling that output down by some factor. I'm using a dynamic lookup table for that purpose. We could have used a simple gain block also, but it works fine with when we run the normal simulation, but as soon as we use external IO ports of the Arduino library, it gives an error. So that's why I've gone with dynamic lookup table here. We'll feed these x data and y data values as an array, so that according to this x, it selects a particular y here and sends it out. It's just a scaled down version of the output given by the joystick. That value we are integrating here. This is a discrete time integrator. This is primarily used because we don't want that as soon as the user relieves the joystick button, the frequency of blinking LED comes back to 0. We don't want that. We want that if the user moves the joystick button in a positive y-axis, the frequency should increase, and if the button is released, it comes back to its normal position. The frequency which was set maintains its value. It does not drop back down to 0. So that's the reason we are using an integrator here. And similarly, when the user gives a negative y value using the joystick button, it does not directly go from 0 to negative value. Instead, it goes down from the previously set value, and based on the extent to which the button is moved along the y-axis, this input to the integrator comes, and the faster the ramp is towards either positive direction or negative direction. That's what the integrator will give as the output. Now this output of the integrator goes to the comparator here and also to this manual switch. This switch sends either positively rectified sine wave or negatively rectified sine wave based on what input it is receiving from the integrator. Now based on whether the user has maintained the joystick button towards the positive y or the negative y, this integrator output will be either positive or negative. If it is positive, this switch sends a positively rectified sine wave. If it is negative, it sends a negatively rectified sine wave. This rectified sine wave is compared with the integrator output. Now here, this is like how a common PWM signal is generated. It's the same basic principle here. We are comparing the reference which the user is giving through the joystick, that is of course integrated, and that we are comparing with the rectified sine. So we get a PWM like signal, and once it is high, it gives a high signal to this red LED, and consequently through this NOT gate, it gives a 0 signal to this blue LED. Again, during its off cycle, the red LED becomes low and the blue LED becomes high. This is how we get alternatively blinking LEDs, and whose frequency is governed by the joystick input and how it is integrated. One thing to be kept in mind is the output of this integrator can go up to plus infinity or minus infinity, because there can be a scenario where the user keeps the switch in the positive y direction or negative y direction for too long. That's why we have saturated the values to plus 100 and minus 100, so that the output of this integrator does not go beyond these limits. Also, since we know that this signal will never cross plus or minus 100, that's why the amplitude of the sine wave is also kept as 100. The frequency is kept as 5 pi radian per second, that corresponds to 2.5 hertz. We can change these parameters as desired. Now we have the joystick input kept at default value 523, which is the normal resting position of the joystick switch. So we'll see how this simulation runs now. Now before starting the simulation, we need to define this xdat and ydat for this dynamic lookup table. We know that the range of values coming to this x will range between minus 523 and 500. So this xdat should be an array ranging from minus 523 to plus 500, and this ydat should be a scaled down version of xdat. So now we will define xdat and ydat in our workspace. Xdat should be an array between minus 523 in intervals of 50, max value can be 500. Ydat will keep simply as a scaled down version of xdat, let's say xdat by 10. So we see that xdat and ydat both are 1 cross 21 arrays. Not sure why this red boundary is still showing, but I think it should run just fine. So we'll start this simulation. Now the simulation is running. Let's open our scope to see our signals. Right now we can see it's 0 and this is 1, and that is because the joystick is currently at its normal position, that is y equal to 0. Let me arrange this. Now we will try to modify this joystick input using the slider control and see its effect. So we can see as we change it, this LED starts blinking, and so does this. This is like a PWM signal whose frequency can be controlled using this slider. As we move it further, we see a change in the duty cycle of both these LEDs. We can move it to the other side. This will give a negatively rectified sine wave, and hence we see a change in the behavior as well as the duty cycle. So I hope this simulation is clear. Next, we will remove these manual inputs and instead use our IO ports from the Arduino toolbox and integrate the model with these ports. Let's move to our Arduino board now. As you can see, we have our Arduino setup right here. On this side, we have analog input pins. On the right side, we have digital out or digital in pins. Some of them can be configured as PWM pins. Now let's take a look at the joystick module. As we can see, here are 5 out pins. The first one is ground and the second is the power supply plus 5 volt. Both of these are taken from our Arduino board itself. VRX and VRY is the analog out signal, which is given corresponding to movement of this joystick button in either plus X minus X or plus Y and minus Y direction. The last one is the switch. If we press this joystick button, this switch output goes as high, otherwise it's low. Now these, although this VRX is connected, we are not utilizing it. This VRY is taken here on the A0 pin as we saw in the model. Also the output, the digital output, is taken from pin number 2 and 3. Pin number 2 is connected to this red wire going to this red LED, and pin number 3 is connected to this blue LED, of course through a resistor. These resistors are 1 kilo ohm each, thereby restricting the current flow through the LEDs because they are very sensitive in nature. They can only support a max current of up to 20 milliamps. Anything above that can damage them permanently. Now our hardware setup is ready. The only thing remaining is generating an executable code out of our Simulink model and then flashing it on our Arduino board. Then we can give our input through the joystick module and observe the output. So let's get to it. Now let us set the configuration parameters from the Simulink model. So I'll bring up the settings now. Here we can see I've set fixed step as the solver selection, and our solver is OD4. The step size I've kept as 0.001 seconds, and in all these blocks wherever required the same step time has been used. Now you will observe that I'm getting a hardware tab here, and this is for the Arduino board that is connected right now to my laptop. But if this is the first time, you might not get this tab. Now in order to bring it, we have to configure the hardware implementation here. So go to hardware implementation. Here we can see the hardware board is Arduino UNO. If it's not selected, you can select this. I'm using UNO, so I've selected Arduino UNO. The vendor will automatically get selected as XML. Next, go to target hardware resources. Here we can see host board connection. Make sure that the host COM port should be selected as the one which is being used by the Arduino board. The baud rate can be set here. It has taken a default value. You can change it also using this drop down. Now since everything is configured here, we click OK. Next we go to the hardware tab. Here we have two options. One is run on board, which is known as external mode. The second is connected IO, that is input output mode. In case we have selected run on board, this means that executable model would be deployed fully on the Arduino board, and it would run on the board irrespective of whether it is connected to the laptop or not. It would be independent of our Simulink environment. On the other hand, if we run it in connected IO mode, then the model and logics will run on Simulink, and only the IO ports of the board would be utilized. This would mean that if we have any external sensor or any input source connected to the Arduino board, or any output connected to the Arduino board, those will be utilized. Let's suppose we have joystick module in this example. So the input from the joystick module will be captured by the Arduino, sent to the model in Simulink, processed there as per our logic, and then the output would be sent again to the Arduino board and to the respective LEDs. That is what is done in connected IO mode, where our Simulink would also be in picture along with the Arduino board. However, we would be running the model on board, which means that we would be generating an executable code out of this Simulink model and then deploying the code or flashing the code on the Arduino board itself, so that the board becomes independent of the Simulink environment. So we select this, run on board. The stop time is infinity because we would want the model to run continuously as long as the user provides inputs through the joystick. Next we have the option of build, deploy and start. So this will build the code from this Simulink model, deploy it on the UNO board and start the execution. So we'll click here. As we can see here at the left hand corner, we can see the model is now currently being built. Once it is built, it will be deployed on the Arduino, and we could identify that it is getting flashed by these two LEDs which are currently off here. Those are RX and TX. So whenever a serial communication happens between the laptop and the board, these RX and TX LEDs will blink. So that is what will happen during flashing. Now as we can see, the code is flashed here. Now our Arduino board is ready with the Simulink logic flashed on the board and the IOs connected. If we vary the reference signal through this joystick, we will see that the blinking behavior of these LEDs will change. We will move this along +y direction. So we can see the duty cycle of the two LEDs changing, and ultimately the frequency of blinking is changing. If we keep it to the max, then we see only blue LED glows, the red one goes to 0, in which case the output of the comparator would be coming as low, and therefore the blue LED is only glowing. If we move it in the negative y direction, slowly the red one starts blinking, and if we keep on moving towards -y, the duty cycle of the on period of the red LED increases. Then we go to the negative cycle. The behavior is inverted again. The blue LED starts glowing for more time duration, and if we keep on going further negative by moving the joystick to -y direction, again we see the change in duty cycle until at the very end only the red LED glows, in which case the output of the comparator would be 1, and therefore the blue LED is low at all times. This is how, by changing the duty cycle using the joystick, we can vary the frequency of blinking of the LEDs. So that is all about this example. I hope this proved to be helpful. In case you have any questions, please drop it in the comments and I'll try to answer them. Thank you for watching. Meet you all in the next video.